Welcome to the second module, the celestial sphere. The celestial sphere is an ancient concept that is still very useful for contemporary astronomy. To your right is a model of the celestial sphere from the 16th century. When looking out on the night sky, it appeared to the ancients that all the stars were fixed on the inside of a very large sphere called the celestial sphere. Common sense suggested to them that the celestial sphere revolves about Earth about once each day. The ancients were aware that the planets, wanderers in Greek, as well as the sun and moon, move with rhythms different from the stars. They also knew the planets were closer than the stars because they sometimes passed in front of stars, never behind. We now know the celestial sphere is actually the projection of a three-dimensional universe onto a two-dimensional surface. Stellar distances are so large and relative stellar motions so small from year to year, allowing astronomers to continue to make use of the important configuration points and features of the celestial sphere. In the contemporary perception of the celestial sphere, Earth is round. This is not a common sense conjecture, however. Earth appears flat to us. To be sure, there are natural undulations, such as mountains or valleys, but the horizon appears flat when observed from the shore of an ocean, for example. From the time of the ancient Greeks, philosophers and scholars were well aware that there was good evidence that Earth was round. It only appears flat to us because the radius of Earth is millions of times larger than the height of the average person, or thousands of times larger than the height of mountain ranges. The relevant evidence for a round Earth includes the following. Lunar eclipses. A lunar eclipse occurs when Earth passes directly between the sun and the moon. This occurs infrequently, but when it does, the eclipse is visible from much of the nighttime side of Earth. In a lunar eclipse, Earth's shadow is always the shape of a circle, or a disk, as shown in this wonderful montage. A circle is, of course, a two-dimensional projection of a sphere. Secondly, the elevation or altitude of any celestial object at a given moment, the angle it appears above the horizon, depends on an observer's location. On a flat Earth, the distant sun would appear at the same elevation independent of the observer's location. On a round Earth, as Eratosthenes conjectured over 2,000 years ago, something we'll discuss more in the history module, the sun's elevation at a given moment depends on the observer's latitude. The elevation change observed is consistent with Earth being round. The fact that the hull of a ship sailing away from port disappears before its mast is strong evidence for a round Earth, as can be seen from this montage and accompanying sketch. One could also add as evidence in this context Drake's circumnavigation of Earth, not to mention the orbit of satellites. And to the right, you see evidence not available to the ancients. Images from space show a distinctly round Earth. Moreover, other nearby bodies, such as the Moon, Mars, and other planets, appear round, particularly through a telescope, and so by an analogy, Earth is round. Perhaps you have other evidence to offer in this context. But it's important to appreciate two things from this exercise, however. First, it is always possible to concoct another explanation for any one of the above observations. For example, consider an alternate hypothesis that seas always get rougher the further one sails from land. If true, this would lead to the hull disappearing first while Earth was still flat. One could then investigate whether this alternate hypothesis is true by having sailors record sea roughness on their journeys from port. Now, the alternate hypothesis is almost certainly false in general, of course. The main point is that the combined evidence as presented provides virtually unassailable evidence, no pun intended, for a round Earth. Second, note that because of the nature of science, there can never be absolute proof for any hypothesis. There can be strong and stronger evidence, just not absolute proof. Now that we have established Earth is round, let us establish how this fits in with the celestial sphere. There are two types of circles that can be formed from the intersection of a plane and a sphere. A great circle is formed on the surface of a sphere by the intersection of a sphere and a plane that includes the sphere's center. A small circle is formed on the surface of a sphere by the intersection of a sphere and a plane that does not include the sphere's center. Lines of longitude, for example, are great circles, while lines of latitude, except for the equator, are small circles. Interestingly, the shortest distance between any 2 points on a sphere's surface is the arc of a great circle. Ideally, planes fly along great circles to minimize distance and hence fuel consumption. This is why planes traveling from Vancouver to Frankfurt, for example, fly close to the North Pole. You will learn that all celestial objects have angular momentum and therefore rotate. Earth is no exception. It has a rotation axis that intersects its surface at the North and South Poles. How is the North Pole distinguished from the South Pole? The North Pole is identified in the following way. Using your right hand, curl your fingers in the direction of rotation. In this way, your thumb will always point north. Arbitrary but important. The equator is the great circle formed on the surface of a sphere by the intersection of a sphere and the plane that includes the sphere's center and is perpendicular to the rotation axis. Two coordinates are required to identify uniquely a point on the surface of the sphere. In the case of Earth's surface, the convention is to use longitude and latitude. The arbitrary 0 point for longitude is the prime meridian, the line of longitude through Greenwich, England. Longitude is measured in degrees, either east or west of Greenwich. For example, Calgary has a longitude of 114 degrees west, while Karachi is 67 degrees east. The 0 point for latitude is the equator. The North Pole has a latitude of plus 90 degrees and the South Pole a latitude of minus 90 degrees. You have here an example of Miami, which in fact has a longitude of just over 80 degrees west, sometimes denoted minus 80 degrees, and a latitude of plus 25.8 degrees north. The extension of Earth's rotation axis intersects the celestial sphere at the North Celestial Pole, abbreviated NCP, and South Celestial Pole, SCP. The extension of Earth's equatorial plane intersects the celestial sphere in a great circle called the celestial equator, abbreviated CE here. Another common great circle that you'll encounter in your studies is that of the ecliptic, the intersection of the Earth-Sun orbital plane on the celestial sphere. The ecliptic plane, or just plain ecliptic, is tilted to Earth's equatorial plane by about 23.5 degrees. And that's the red circle you see on the image to the left. On a clear night, approximately half of the celestial sphere is visible in principle to an observer at any one moment. Earth blocks or occults the other half. We refer to the boundary between Earth and celestial sphere as the observer's horizon. The observer's true or astronomical horizon is the intersection of a tangent plane on Earth's surface at the location of the observer with the celestial sphere, as illustrated in this slide. At any moment, half of the celestial sphere is above the horizon, half below. The apparent horizon is the intersection of the observer's line of sight with Earth's surface, as projected onto the celestial sphere. The distance to the observer's horizon depends on the observer's height above the surface and Earth's radius, as you can see from this figure. The zenith is a point on the celestial sphere directly above an observer. It is the intersection of a line from Earth's center through the observer to the celestial sphere. The nadir is the point on the celestial sphere directly below the observer. It is the intersection of a line from the observer through Earth's center to the celestial sphere. The observer's celestial meridian, or meridian, is a great circle on the celestial sphere that passes through the north celestial pole, south celestial pole, and the observer's zenith, and nadir, of course. It divides east from west in the observer's sky. The part of the celestial meridian above the observer's horizon is called the upper meridian, while the part below the horizon is called the lower meridian. The horizon coordinate system offers a natural coordinate system for an arbitrary observer. It uses the azimuth and altitude coordinates to uniquely locate an object on the celestial sphere. The azimuth is the angle along the horizon from north through east, from 0 degrees through 360 degrees. An object due south, for example, of an observer has an azimuth of 180 degrees. Due east, 90 degrees. Due west, 270 degrees. The altitude is the angle measured from the horizon along a line of constant azimuth to the star or celestial object. The horizon has by definition an altitude of 0 degrees, while zenith has an altitude of plus 90 degrees and nadir minus 90 degrees. By the way, the angle between a celestial object and an observer's zenith is called the zenith angle or zenith distance, abbreviated Z or Z. This becomes important when dealing with things such as refraction of the atmosphere. And of course, the zenith angle or zenith distance is just 90 degrees minus the altitude of an object. Try to work out the azimuth, capital A, and altitude, small h, for the 3 examples given at the bottom of this slide. This concludes the celestial sphere module.